Hello everyone, welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Shetrumayam. So, in this class, we'll discuss about the spherical waves. We'll discuss about the plane waves, cylindrical waves. Now we'll discuss about the spherical waves. We have done a lot of preparation for this. So now, in this spherical waves like cylindrical waves, we will consider the case for TER and TMR spherical waves. So TER means transverse electric along the R. That means we will not have electric field along the radial direction. TMR means transverse magnetic along the radial direction. So we will not have magnetic field along the radial direction. For TER spherical waves, the condition for the TER spherical waves is your F vector should be having only radial component. F vector will be simply FR R head, and A vector should be equal to 0. So what is the condition for the spherical waves TER case? F vector will have only radial component FR and A vector should be 0. In that case, you can also observe that electric field was represented as minus 1 by epsilon curl of F. So when I do curl of F and F is having only radial vector, in that case ER should be equal to 0. So this satisfies the condition that electric field will not have any radial component. We can solve the wave equation for F vector in a source-free region. We have already discussed that in the previous class. The wave equation was curl of F minus omega square mu epsilon F is equal to minus j omega mu epsilon del phi m. That was the wave equation we have derived in the previous class. We'll solve this now for the TER spherical waves. And when we solve it, after doing some mathematical manipulations, you'll observe that this wave equation gives wave equation which is Helmholtz wave equation like del square plus beta square Fr by R is equal to 0. So the previous wave equation for source-free region, when we have TER spherical waves with F is equal to Fr component, A is equal to 0, what we are getting is that the Helmholtz wave equation is satisfied by Fr by R. So it's not Fr, it's Fr by R, which is satisfying the Helmholtz wave equation. Is that okay? We are getting a result that shows that Helmholtz wave equation is satisfied by Fr by R. This is little bit different than whatever we have done for plane waves and cylindrical waves. Their wave equation was satisfied by one of the components of the fields. But here the wave equation, Helmholtz wave equation, is satisfied by Fr by R. We have one additional term R here, Fr by R. Okay. So now let's summarize what we have seen in this slide. What we have seen is that for TER spherical waves, F vector will have only Fr component and A vector will be 0. And one more very important observation is that Fr by R will satisfy the Helmholtz wave equation. So now if we solve the Helmholtz wave equation and find electric field will have contribution from EF and EA. That's the discussion we have done in the previous class. Electric field will be found out from the F vector and A vector, and we will have contribution from both F vector and A vector. So this is a contribution from the F vector and this is a contribution from the A vector. Similarly, magnetic field will also contribution from F vector and A vector, and this is contribution from F vector and A vector. Now in this case A was 0 when we considered which kind of wave we have considered? We have considered TER waves. For the TER waves, A vector is 0. In that case, the second term here and second term here won't contribute anything. So let us solve the Helmholtz wave equation for a scalar function psi. So this scalar function psi could be Fr by R or Ar by R depending on whether we are considering TER waves or TMR waves. If we are considering TR waves, the psi could be Fr by R, or if we are considering TMR wave, the psi could be Ar by R. So we'll find a generic solution by considering a scalar function psi, which could be Fr by R or Ar by R for TER or TMR waves. So let us summarize it. What we are trying to do, we want to find the Helmholtz wave equation for psi, which could be Fr by R when it is TER wave or Ar by R when it is a TMR waves. Once we have that psi, which could be Fr by R or Ar by R, from there we can find electric field and magnetic field by using this relation. Electric field will have contribution from the F vector, A vector. Magnetic field will have contribution from the X vector or A vector. So we find the Fr by R or Ar by R and use this relation to find the electric field and magnetic field. So let us try to solve the wave equation. Del square psi plus beta square psi is equal to 0. This is generic wave equation for the spherical waves. So obviously the coordinate system we'll be considering would be spherical coordinate system. So by the way, what was the Laplacian in the spherical coordinate system? And I have discussed in detail what is the Laplacian in general curvilinear coordinates. And as I have already told you before also, it's very easy to remember this Laplacian in the general curvilinear coordinate system. Once I have the Laplacian in general curvilinear coordinate system, which is this expression 1 by s1, s2, s3, first term, second term and third term, all I need to do is replace scale factors and the coordinates. Scale factors for the spherical coordinate system is 1 r sine theta. Coordinates, a1 is r, a2 is theta, a3 is phi for the spherical coordinate system. In that case, this wave equation would now become simply like this. I just replace a1, a2, a3 by r theta and phi, s1, s2, s3 by 1 r sine theta. So this is the wave equation we are getting. So if you multiply by r square sine square theta in both sides, this is the wave equation simplified we are getting. So now, as usual, we have done for plane waves and cylindrical waves. The method we apply for solving this wave equation is method of separation of variables. So here I represent this psi as a product of three functions r, capital theta and capital phi, where capital R is dependent on R, capital theta is dependent only on theta, capital phi is dependent only on phi. So I've separated out the dependence of psi with respect to r, theta and phi as product of three functions. So when I do that, look at this partial derivative with respect to r. So now when I do partial derivative with respect to r, or let's say when I do partial derivative of psi with respect to r, only this capital R is dependent on the r. So this capital phi and capital theta are independent of r, so we can take it out, it's a constant. Similarly, when I do partial derivative with respect to theta of psi, only capital theta is dependent on theta. R and capital phi can be taken out. And when I do partial derivative with respect to phi of psi, only capital phi will be differentiated, and capital R and capital theta can be taken out. They're independent. They're just like a constant. So the wave equation simplifies after applying the method of separation of variables. So if we divide by product of capital R, capital theta and capital phi in this equation, then the wave equation simplifies like this. So now look at this term here. This term is totally dependent on phi, and what you can observe is first term and last term are dependent on R, and second term is dependent on theta. So in that case, this term you can equate it to a constant. We equate the third term to a constant minus m square, and minus m square is an arbitrary constant. So the wave equation now simplifies to this. I replace 1 by capital phi del square phi by del phi square by minus m square. So now looking at this equation, after multiplying sine square theta everywhere, after dividing by sine square theta everywhere, what do I get? When I divide by sine square theta everywhere, what I'm getting is the first term is totally dependent on R. The last term is totally dependent on R. And second and third term are dependent on theta. So now in that case, I can convert this wave equation into two separate equations. One for the R, we assume that the term which are dependent on R is equal to n into n plus 1. And the term which is dependent on theta, two terms were there, I assume it's equal to minus n into n plus 1. When I sum them out, total will be equal to 0. So n into n plus 1 is an arbitrary constant. So I can still do that. So now I can rewrite this equation by multiplying by R and transferring this term to the left hand side. This is the equation we are getting. This equation is the spherical Bessel's equations. So spherical Bessel's equation, you know that it will have two solutions. Let's discuss the first solution. In the first solution, capital R will be combination of Jn and Yn. So Jn and Yn, what are these Jn and Yn? Jn here and Yn are in the small letter symbols. These Jn and Yn are called the spherical Bessel's functions of first kind and second kind. J and Yn are the spherical Bessel functions of first kind and second kind. This spherical Bessel's function actually represents radial standing waves. We'll consider another solution in which the solution will give me propagating waves, but here Jn and Yn are radial standing waves, and they are also related to the regular Bessel's function. We have discussed regular Bessel's functions was a solution for the cylindrical waves. So now for the spherical waves, spherical wave equation, the solutions are spherical Bessel's function. There is some relation between these two. You can always obtain these spherical Bessel's functions of first kind from the regular Bessel's function of first kind. What you need to do is you need to multiply by square root of pi by 2 beta r, and the order should be changed to n plus half. Similarly, if you want to get spherical Bessel's function of second kind Yn, you need to multiply by square root of pi by 2 beta r. Then this should be n plus half. So now, what was the variation of J and Y with respect to rho? It was 1 by square root of rho. That was the signature for the cylindrical waves. But now for the spherical waves, since I am multiplying by 1 by rho, 1 by square root of 1 by r, already Jn plus half was having a variation as 1 by square root of 1 by r. So when I multiply these two, what I'm getting is 1 by r. So J and R variation with respect to r is 1 by r. Y and r variation with respect to r is 1 by r. So that's the signature for the spherical wave. The variation of the waves with respect to r should be 1 by r. That's what we're getting here. The second solution is actually for the propagating waves. We can represent capital R as a combination of Hn1 and Hn2. Here again we have a small letter. It means that this is a spherical Helmholtz function of first kind and second kind. This spherical Helmholtz function of first kind and second kind are related to the regular Helmholtz functions by this relation. If I want to get Jn beta r, I just multiply by square root of pi by 2 beta r with Jn plus half beta r. Similarly, if I want to get Yn beta r, I just multiply by square root of pi by 2 beta r with the Yn plus half beta r. So here you can also observe that the wave is varying with respect to distance r as 1 by r. That's the signature for the spherical waves. We are getting it here also. And this Jn and Yn are radial propagating waves. This would be Hn1 and Hn2. This would be Hn1 and Hn2. This would be capital Hn1 and capital Hn2, n plus half, n plus half. So Hn1 and Hn2 are radial propagating waves. Jn and Yn are radial standing waves. We have another equation which is, you can observe that is the Legendre's equation, and the solution for the Legendre equations is associate Legendre functions. And the solution capital phi is actually a combination of Pnm cos theta and Qnm cos theta. What are Pnm cos theta and Qnm cos theta? These are the associate Legendre functions of first kind and second kind. N is the degree, m is the order. We have two parameters here. One is n, another is m. N is the degree and m is the order. Here E1 and F1 are any arbitrary constants. One important point to be noted is that Pnm cos theta is finite at theta is equal to 0 or pi only if n is an integer. See, the solution we have for the wave, let's say inside a sphere, cannot have infinite value of fields. Infinite value of fields is impossible thing. So most of the time we want finite values of the field. For finite values of the field, if we want to have finite values of the field for Pnm cos theta for all values of theta, then n should be integer. Otherwise, if n is not an integer, then Pnm cos theta is going to have an infinite value at theta is equal to 0 or pi. So the solution we would be interested is when n is an integer, because we cannot have infinite fields anywhere. Similarly, Q and M also tends to infinity when theta is equal to 0 or pi for any value of n. So if Q and M has a discontinuity at theta is equal to 0 or pi by having an infinite value, we cannot have such kind of solution for physically realizable waves. For physically realizable waves, we cannot have infinite fields anywhere. So this solution is ruled out most of the time. This solution is possible only when n is an integer, because we want to have finite value of this when theta is equal to 0 and pi. So we want to consider case when n is an integer. So that means n can take values like 0, 1 and 2. In that case, we call this Pnm cos theta as associated Legendre polynomial. We no longer call it as a function, it becomes a polynomial now. And we can obtain this associated Legendre polynomial from the Legendre polynomial Pnx for the range when m is in between minus n to plus n. And this is the formula for finding the Pnx from the Pnx. Pnx is the associated Legendre polynomial, Pnx is the Legendre polynomial. If I want to find Pnmx from Pnx, I just need to differentiate it. So I multiply by minus 1 to the power m, 1 minus x squared to the power m by 2. I do the differentiate d to the power m divided by dxm of Pnx. Then I get the associated legendary polynomial of degree, and m is the order. M is the order, n is the degree. So m is the order of derivative of Pnx with respect to x. When you assume that m is equal to 0, if m is 0, then this turns out to be your regular legendary polynomial. When m is equal to 0, associated legendary polynomial becomes legendary polynomial. If you want to get legendary associated legendary polynomial from legendary polynomial, you need to differentiate it like this. Legendary polynomial can be easily obtained from the Rodix formula. If I want to get Pnx, I just do differentiation of dn by dxn of x squared minus 1 to the power n, and multiply by 1 by 2 to the power n by n factorial. I get the legendary polynomial. Here n is the degree, m is the order. N is the degree of derivative we are doing with respect to x squared minus 1 to the power n with respect to x. Pnx is a polynomial of degree n. See, this Pnx can be obtained from the recurrence relation also, but we'll not discuss that in this class. If you want, you can explore. And one more observation is that this Pnx will have an orthogonal set of polynomials in between minus 1 to plus 1. So we have got all the solutions of the psi. Psi has three components. It's the product of three functions r, capital theta, and capital phi. So we want to discuss about the typical solutions of psi. What are typical solutions of psi? Let's say if I want to find fields inside a sphere, and I need to have finite fields at r is equal to 0 and theta is equal to 0, pi. In that case, psi will have solution like this. Any constant Cmn1 Jn beta r Pnm cos theta into C1 cos m phi plus D1 sin m phi. Or let's say if I want to have fields outside a sphere, but finite fields at r is equal to 0, theta is equal to 0 and pi. In that case, psi will have solution like this. Any arbitrary constant Cn2 is n2 beta r Pnm cos theta into C1 cos m phi plus D1 sin m phi. So in this class we have discussed about the solution of the wave equation, and this solution will be helping us to find the fields for TER and TMR case. And we have observed that the Helmholtz wave equation is satisfied by AR by R or FR by R. Once I have AR or FR, I can find electric field and magnetic field from the relation we have derived in the previous class. So here we have solved the spherical wave equation, and we are getting the equation for the spherical waves. And we have observed that signature of the spherical waves, the variation of electric field or magnetic field with respect to R as 1 by R, is satisfied for the solution we have considered. Thanks for your attention. Hope to see you in the next class.